So let's have a look at this idea of related rates of change. We've seen it before, but it's when we can combine two or more rates to find another rate. So it uses, well, the chain rule, implicit differentiation, whatever you want to call it, it's all the same idea. So let's have a look at an HSC one. So 2017, stone drops into a pond, creates a ripple. Radius of the ripple starts at 0 and then moves out at a rate of 5 centimetres per second. At what rate is the area of enclosed of that ripple increasing when the radius is 15? So we're trying to find dA to t, rate of change of that area with respect to time. But they've given me dr to t, rate of change of the radius of the ripple. So how can I link these together? Well, if I can work out an expression for dA dr, then we have the link that will allow us to solve this problem. So a relationship between A and R, which of course we do have for a circle. We know area is pi r squared. So dA dr would be 2 pi r. We can now complete our formula. So we end up with 5 times 2 pi r. So 10 pi r is the formula for the rate of change of area. Now we want to know when that radius is, where is it? It's there somewhere. There it is, 15 centimetres. Sub it in, we get 150 pi. And so to finish off, we answer the question. So the ripple's area is increasing at a rate of 150 pi, and that would be centimetres squared per second. This one, it was quite a good question. So we've got a Ferris wheel, radius 20. It's rotating at 1.5 radians per minute. Top of the carriage is h metres above the horizontal diameter. The angle of elevation of the top carriage from the centre is defined as theta. So the first part of the question was just to simply come up with this rate. That dh to theta was 20 cos theta. So we need a link between h and theta, and that's just using that right angled triangle we can see there. So h over 20 is sine theta. So h is 20 sine theta, dh to theta, 20 cos theta. At what speed is the top of the carriage rising when it's 15 metres higher than the horizontal diameter of the Ferris wheel? So we want to find the rate of change of h. dh to theta is 20 cos theta, we just worked that out. So how can we link these two? Well, there is an expression there for the theta to t. It was 1.5, what were our units? Radians, of course, because theta's an angle. So 1.5 radians per minute. Well, I've changed that to a fraction. Combining that together, we come up with our new formula that dh to t is 30 cos theta. So when h is 15, there's our triangle. So we can actually work out what the cosine of theta is, rather than worrying about finding the angle. A bit of Pythagoras there, root 175 for the other side. So I can read off that, 30 times root 175 on 20, 19.843. So there we are, it's rising at a rate of 19.8 metres per second. All right, let's go to the next year. This was a little bit different. Distance A is inversely proportional to distance B, such that A is 9 over B. And the two distances also vary with respect to time. Distance B is varying at a rate of 0.2. So what will be dA to t be when A is 12? Okay, so what do we get out of that? We've got to find dA to t. And what have we been told? Well, we've been told dB to t. Now we need that link between A and B, and they've given us that. So A is 9 on B. So therefore, dA to t, well, derivative with respect to B, so it's dA to B, would be minus the derivative on the function squared. I just went and did that straight away rather than writing it down there. But minus 9 on B squared times dB to t. We want to know when A is 12, so then B is 9/12. So now we can sub in. So minus 9 on B squared, B is 9 on 12, so I've inverted there and multiplied, 144 and 81, times the dB to t, which is 1/5, and we get it out eventually, minus 16 on 5. So A is decreasing at a rate of 3.2 metres per second. So that's all that idea. What are we trying to find? What information do we have? How do we now link them together? Okay.